Welcome to Learning Functional JavaScript Section 5, Immutability. In this section, we will focus on a functional approach to data types, immutability. We will see how to design programs in a functional way around immutable types and how to work with immutability in the UI. This is video 5.1, What is Immutability? This section is about immutability, values that never change. In this video, I will explain the difference between mutable and immutable values and why we might want more of the values that don't change in our programs. In the following videos, we will learn to work with immutable values and see a couple of examples where they really shine. Immutable values are values that can never change once they've been created. If this seems strange or inflexible to you, consider these values. Let's say that we'd like that name in all uppercase. We call the toUpperCase function and it returns the name in all uppercase letters. What it is not doing is changing the original string. After calling that function, we have two strings, the original one and the new one, which is in all uppercase letters. If you've worked with JavaScript for some time, this behavior should not surprise you. But have you ever stopped to think why it's so? The reason is that strings are immutable values in JavaScript and many other programming languages as well. A string cannot be changed, you can only ever produce new strings. Let's consider another example. Numbers are also immutable in JavaScript, and for good reason. Can you even imagine the chaos that would ensue if calculating the sum of the numbers 2 and 3 would change the meaning of the numbers themselves? It sounds preposterous, yet this is what we do with most objects in our systems all the time. Consider yet another example. If arrays had the same semantics as strings and numbers, we would expect that val2 in this case would contain a new array with the numbers 0 through 3, and that the arr variable would contain the original array with the numbers 0, 1, and 2. This is, as I'm sure you're aware of, not the case. As we can see, val2 contains the number 4, the new length of the old array. The arr variable still points to the same array as before. The push method has mutated, or changed, the array so it now contains all the 4 numbers. The original version of the array has been lost in the process. The problem with mutable data types is that the mutations are destructive. We lose track of previous state. It's not uncommon in a system of mutable types to ask the question, how did we get to this state? If mutations happen throughout the codebase and the history of changes are not preserved, reasoning about state can be very challenging. In addition to this practical problem, mutable objects pose a philosophical problem. If a person celebrates their 33rd birthday, does that mean that the person was never 32? Of course it doesn't. We may or may not care about it in our program, but representing the state as a mutable object means we have to work very hard to keep track of history as time progresses. With mutable objects, data loss is the default. So JavaScript arrays and objects are rife with mutation. How do we go about building immutable lists and objects? Well, a manual approach could look like this. Calling the slice method without any arguments basically gives us a copy. We can then mutate the copy to add a new number. Abstracting the details away in a function would make it look a little bit less messy. Using this gives us something akin to the string and number examples from before. In other words, we could treat our mutable arrays as immutable and design a library of functions to operate on them without mutating them. However, this would be a fairly brittle solution, and a quick misstep could mess it all up. Another approach would be to design entirely new data structures and use those instead. The list function encapsulates the contents and offers a read-only API. In order to build new derived values, we would need things like push as well. Following this model, we could even provide a function to set the value at a specific index, only it wouldn't change the original list, but provide a new list which is exactly like the original, except with a new value at the specified index. You get the idea. you might be thinking that this looks rather inefficient. And at a micro benchmark level, it does. Allow me to suggest an improvement to the current implementation. If trying to set the same value already in place, we don't need to produce a new list. We can just return the existing one. Because it will never change, there's nothing to worry about. That's a good optimization, and it opens the door to more optimizations. Now we have 3 lists, and 2 of them contain the same values. If these were arrays, we need to loop them both in order to know if they represented the same list of values or not. With our immutable list type, we can simply do a reference equality check. This means that immutable values, while less efficient in some areas, will be able to provide huge benefits in environments with lots of change tracking. As we'll see later, UIs do a lot of change tracking. Note that if the list can come from any source, we would still need to compare them element by element. For the remainder of this section, we will not be building out our own immutable types. Instead, we will use a full-featured library from Facebook, aptly called Immutable.js. This library has many interesting immutable data types and a rich API to work with them. It also features a very interesting implementation which is way more performant than the naive approach taken here. We'll get back to that. In this video, I've shown you what immutability is, why it may be easier to reason about than mutable values, and given you a peek of how it can be implemented. In the next video, we will write some code with immutable values.